All right. So, hope you all had a nice weekend. Today, join me in welcoming Kris De Asis. He's also a PhD student at the RLA lab, and he's going to tell us about inverse policy evaluation for value-based decision making. Take it away, Kris.
Yep. So hi everyone, I'm Chris, and this is going to be about inverse policy evaluation for value-based decision making. And this is joint work with Alan Chan. So if you're familiar with policy evaluation, this is probably exactly what it sounds like. And at the same time, it's not really clear why you would ever want to do this. And when Alan and I have been trying this out, it seems to be doing something. And most of this talk is trying to tease apart what exactly it's doing. So I guess to give a bit of background, this is for a reinforcement learning setting where you've got some agent in some state. It takes some action, and the environment will produce a new state along with some reward signal that you can use to inform your decisions. And in particular, these actions are drawn from some policy, which is a probability distribution over actions. And the policy is usually learned in a way that tries to maximize returns, which are defined to be these discounted sums of rewards. And in particular, this is going to be about value-based methods, and they approach the problem by trying to predict what the return will be. So they define these value functions, which are expectations of this quantity conditioned on certain things, like the state value function V is conditioned on the current state, and the action value function Q is conditioned on the current state and some immediate action. And in particular, once you've estimated these value functions, they try to use them to improve a policy using the policy improvement theorem. So for value-based decision-making, if you assume that your values are accurate, if you greedify with respect to some policy's value function, you produce some improved policy, and you would repeat this process until you reach the optimal policy. And behavior is typically chosen to be some softened greedy policy, for example, epsilon greedy, or some Boltzmann policy over your action value estimates. And this is to account for things like estimation error or the fact that you haven't converged yet, and you're still in the process of learning and collecting more data. Now, policy evaluation is where you're given some target policy, and it's the goal of trying to estimate these action values as accurately as possible. So to picture this, you've got a policy going in and some value function coming out. Now, inverse policy evaluation is exactly what you'd imagine, where given some value function estimate, what policy does it actually correspond to? So with that same image, Q goes in, policy comes out. And now, how would you do this? If you have some value function, how would you find the policy that actually corresponds to it? And in particular, the approach we used was to make use of the Bellman equation for the action values, where we know that under Markov assumptions that the value functions have to satisfy this relationship where you can express the value in terms of the values of successor states. And so we can see that a policy term shows up in this equation, and you can instead fix the value function and try to find the policy which makes the values best satisfy this relationship. And so one way you can do this is to rearrange these terms, maybe square it, and then minimize it. So if you were to use some squared loss over this relationship, we would get the following sample-based update, where you've got your usual TD error delta here, and in particular, this is expected Tarsus TD error, where it's the expectation under this parameterized policy pi, and the update is the second line here. And something that you might notice is that this looks like an all actions policy gradient, but it has this extra delta term there. And this delta term is actually flipping the sign of this policy gradient, determining whether you're climbing or descending the gradient based on whether you're over or underestimating your value function or your return. And so this can also be viewed as some policy gradient for matching a value function's proposed returns instead of trying to maximize values or maximize expected returns. So we have this way of finding the policy that corresponds to a value function, but again, why would you want to do this? Why do you want the policy that corresponds to some arbitrary value function? But some immediate observations with this is that a value function can correspond to several policies, but empirically we found that this didn't really seem to be an issue. And if it was, we could probably introduce something like entropy regularization to break ties. And another observation is that a value function might not represent any policy, because the value functions form some polytope given some MDP, and it's possible that with value-based methods specifically that the values are outside of this polytope, and we'll talk about that more later. So now, if we were to invert invert some value function and get its policy, like how can we use that for control? Because that is some policy for some arbitrary value function, and might not be useful for decision making. So instead, we can like use that same picture and imagine that if the optimal value function went in, we would get the optimal policy out. So we have a bunch of methods that can try and estimate Q star directly, such as Q-learning or any approximate value iteration method. And if you were to interleave these inverse policy evaluation updates with those of value iteration, you can eventually approach the optimal policy or track this path towards optimality as your estimates are learned. So to give some intuitions for what's going on, a tabular optimal policy is often deterministic unless there are ties in which that it'll be some mixture of these optimal policies. And under this intuition that it's generally deterministic in the tabular setting, if you have inaccurate estimates of the optimal value function and they don't really satisfy the Bellman equation, the inverse policy evaluation policy likely won't be optimal, and it will tend to be stochastic because the optimal one would generally be deterministic. And so in some ways, this is estimation error aware in that the suboptimality and stochasticity reflects how well the value estimates satisfy a Bellman equation. And so it's one thing that you could do with this is you could use it for hyperparameter selection, because some hyperparameters have these probabilistic interpretations, and intuitively they do depend on the accuracy of value estimates. For example, the degree of bootstrapping lambda in TD lambda, or epsilon and epsilon greedy. And so if the inverted policy's stochasticity is related to the accuracy of the value estimates, its entropy could be used to inform the parameter selection. And specifically, we tried this example where we took epsilon greedy, and we would try and adapt epsilon to match the entropy of the inverted policy of some value function. And we denoted this epsilon IP from here onwards. Now, some other intuition is that it has this sort of on-policiness to it, where normally when we behave with some soft greedy policy, we end up being on policy or approximately on policy with respect to what is ultimately trying to be estimated. So with some value iteration method with epsilon greedy, it's sort of approximately on policy with respect to the greedy policy, because Q star sort of represents the values under the greedy policy. So you're approximately behaving under what you're trying to estimate. But instead, if you behave under this like IP policy, you end up being on policy with respect to the current estimates, which are approximately on policy with respect to the next value estimates after, like as you're doing this like value iteration process. And to sort of illustrate this, like this is the value function polytope for some two-state MDP, where we've got the values along this axis, and this shape here represents the space of all value functions that actually correspond to a policy. And imagine that you have some behavior policy that corresponds to this point here. Now, intuitively, like this isn't always the case, but in a lot of cases, like if you're following some policy, it tends to be convenient for learning a bunch of learning values of similar policies to that one, because you would see similar states, you would see a bunch of returns that are very likely under those other policies. So this gray area might represent like the set of policies that are very convenient to learn, given that you're following this behavior policy. Now, if we say that we're starting with these value estimates in blue here, and we're following an epsilon greedy policy. Now, epsilon greedy would generally follow some policy that's near one of the corners of this polytope, because these are the deterministic policies, and the optimal policy is in the top right corner. So like it would be snapping back and forth between these green dots here. And you can see that this might tug the value estimates in random directions. It might lead it off on some tangent based on like what values are higher than others at that point in time. Now, if we were to instead use the inverse policy evaluation policy, like the dot would coincide with the value estimate, and that region of policies that are easier to learn ends up being around that value function. Now, imagine, like assuming that your values aren't changing too fast, like the next value function will likely lie within that circle, and then your policy would then move to that point, and you'd have a new region of policies that are easy to learn, and you could keep repeating this process until you track your way to the optimal policy and optimal value function. Now, this is very hand wavy and kind of vague, because there's a lot of other nuances where like this policy will affect what you see and what value updates you perform. But this sort of gives some intuition for why this might be a good path to follow, or why it might be useful to base your decisions on this policy. So to make things a bit more concrete, we ran a lot of experiments on this two-state switch state MDP, where you've got two states and you have a choice of either staying in that state or switching to the other state. And it's visualized on the left there, but more importantly, we have its value function polytope on the right. And that's where we visualize most of the dynamics of this policy. So like, given this environment, like the first thing we did was to visualize the policy entropy. So we would sweep over the space of value functions and we would solve for the corresponding inverse policy evaluation policy. And then we would compute and plot that policy's entropy. And this is to confirm that intuition where if your estimates are poor, it would tend to be stochastic. So the map ends up looking something like this. And we can see that like the brighter colors means higher entropy and more stochasticity. And you can see that if you're outside of the polytope, but you're still kind of near it, it does tend to be stochastic. And there are these really dark regions in the corner corresponding to deterministic policies. And intuitively, the reason that happens is because like one value is severely dominating the other value, and then it tends to just throw all of its mass onto that, because that's the best way to satisfy the Bellman equation in those scenarios. But empirically, we found that like due to not solving for the complete policy directly and just taking like one update of inverse policy evaluation along with stochastic updates, like this didn't really seem to be an issue empirically. So the next thing we visualized was the value map, where again we swept over value functions, and then for each of these points we would solve for the policy corresponding to that value function, and then we would compute the true values of that inverted policy. And then we would then show how the values outside of the polytope map back onto it, just to see like if there was some interesting projection being performed by this process. And for value functions near the polytope, it ends up looking like this, where we can see that generally it seems to snap back to a point that's sort of nearby on the polytope. And so it is sort of mapping back in a sensible way instead of just mapping to a completely arbitrary point on the polytope. Like, we weren't really too sure what else we can infer from this, but we thought it was interesting to visualize and see what's actually going on behind this. Now, for learning dynamics, all of these things that I'm about to show you are using Q-learning under the hood. And the thing that's changing between them is the behavior policy. So on the left here, we have inverse policy evaluation, where we're performing like one step of inverse policy evaluation for every step of Q-learning. And in blue, we're visualizing the value estimates learned by Q-learning. And in green, we're visualizing the true values of the policy that it's following. And these red circles indicate the initial values used. So on the left here, we see that like if you follow the inverse policy evaluation, like the policy takes a smoother path towards the optimal policy, but that might be expected because it's a parameterized policy and it's doing something policy gradient-like. And if we look at epsilon greedy, it tends to spend more time outside of the polytope and seems to just get snapped in these different directions. And if you look at the green dots, you can see that it is just jumping around between these semi-determinate or these near deterministic policies, depending on your current value estimates. But you might think that it's not really a fair comparison because this is using a fixed epsilon, whereas inverse policy evaluation is still like adjusting its entropy as it's learning or as it's like iteratively trying to compute this policy along with the value estimates. So we also tried annealing epsilon, and it ends up looking like this. And it does look better in terms of like staying close to the polytope, but you can still see those jumps in the value estimates of the behavior policy because it's still interpolating between these greedy policies, and like it jumps around based on like when when the best value starts to switch. And yeah, so the next thing we tried was epsilon IP, where we would like compute the inverse policy of the value function, but instead of behaving according to it, we would try and adapt epsilon greedy to match the entropy of that policy. And we would behave according to epsilon greedy. And it ends up looking like this. And I thought this was surprising because this is doing epsilon greedy under the hood, but just because we were adapting epsilon according to this inverse policy evaluation, like it ends up following a much smoother path on the polytope, even though these value estimates correspond to those of an epsilon greedy algorithm, just with a dynamically changing epsilon. And to see what was actually going on with this, we plotted the epsilon values that were actually used along this path, and it ends up looking something like this. And typically in a lot of papers out there, when people are using an annealing epsilon, they would usually do this annealing or this linear annealing strategy, where it would like start from some value, or it would start from a high epsilon value and then linearly anneal to some low value and then stop there. But as we can see from this, it ends up following this more sigmoidal shape instead of like an exponential or a linear function. And we did play around with like other annealing strategies like exponential decay or hyperbolic, and they still didn't perform as smoothly as this. So we thought that was really interesting. And we further looked at the sensitivity of these algorithms to their parameters. So this is still on the two-state switch state MDP, and plotted on the left is the average reward accumulated over 500 steps, and on the right is the root mean square error in the value estimates. That is like how accurately it's estimating Q star. And so on this slide, we're showing the two epsilon greedy strategies, where we have a fixed epsilon and annealing epsilon. And the y-axis represents like either the fixed epsilon value or the number of steps to reach the final epsilon value for the annealing epsilon. And in general, to view these plots, like a lighter color is good and a dark color is bad. So like we can see that like the trends are generally reversed here for epsilon greedy, where if we want a high average reward, we settle for a poor estimation error. And if we want really good estimation accuracy, we end up with a worse reward because we're exploring more. And so there ends up being this like really narrow region where it's doing okay at both. And this seems to be the region where you can kind of trust that it's like not a fluke, because it has like good value estimates and it's achieving good reward. And it's not just like some problem dependent thing where it happens to be doing well because it doesn't need really accurate values and just needs to know which is the best action. Now, if we were to do the same thing for inverse policy evaluation, we've got inverse policy evaluation on top and epsilon IP on the bottom, where it's still epsilon greedy, but with the adapted epsilon. And again, on the left is average reward, and on the right is the root mean square error of the value estimates. And like the y-axis is the step size of the inverse policy evaluation process, because like that ends up being the free parameter or the tunable parameter here. And like the main takeaway from this is that the trends in the average reward and the RMS error tends to be in the same direction here. And there's a lot of overlap between the parameters and between these regions, where it's balancing both the estimation error and collecting a lot of or having a high average reward. Whereas with things like epsilon greedy, there was a very clear trade-off where either you were collecting a lot of reward or you were having really good estimation accuracy. And yeah, so all of those were in this two-state switch state MDP, or this tabular environment, but a lot of people care about deep RL, so we ended up trying this on lunar lander. And generally, we found that if you were to behave under the IP policy, it ended up being very sensitive to the parameterization of the policy. So we didn't end up fiddling with it too much, and we instead tried epsilon IP on top of DQN. And it was much less sensitive to it because like it didn't really depend, or it didn't really need the exact policy, but rather just needed some statistics about the policy, like how stochastic it ended up being. And it ended up like fluctuating a lot less than DQN and generally had more monotonic improvements. But like we tried it in a bunch of other environments, and generally it like performed on par with DQN and sometimes looked a lot more stable. So I guess to quickly summarize, like inverse policy evaluation can be used to derive behavior from some value function in some seemingly estimation error aware way. And it could be coupled with approximate value iteration to solve control problems in both online and offline settings. And for some future directions, like we could try exploring other objectives in place of the squared loss. For example, you could use the absolute error. And from the connection to the policy gradient methods, you could further incorporate these policy gradient tricks into the update rule, such as like baselines, the use of some trust region, or entropy regularization. Like we didn't really try a lot of these extensions. We just used the raw IP update in most of the work that we did. And this also could be a useful regularizer where, in addition to improving some policy with some standard policy gradient method, you might do this on the side so that the policy tries to stay consistent with its value estimates on top of trying to improve on them. And yeah, that's mostly what I prepared for today, and yeah.
Yeah, so if folks have any questions, now is the time.
Can you go over the iteration process again? So
The
we
iteration
calculate the Q function and then the policy. I think it was in the beginning. Right, this one.
Yeah.
No,
So,
sorry, not this one.
wait,
Yes.
this part.
Yep.
Okay. So, like, we view this as sort of like analogous to generalized policy iteration, where you interleave policy improvement and policy evaluation at any level of granularity. And similarly, you can interleave value iteration and IP at some other level of granularity. And in particular, in everything we implemented, we would do like one Q-learning update and then one IP update, and just keep alternating those for every transition it sees. But you could do this in like different levels of granularity.
So instead of a greedification, there's an inverse policy evaluation.
Yeah, like we rely on value iteration for doing all of the greedification, and then we're just sort of tracking the value function in a way that seems like it's convenient for learning the value function.
Oh, and why would it work? Can you again give the intuition?
Well, the way that I picture it is that if you're following the policy that corresponds to some value estimates, it ends up being really convenient for learning the value function that is nearby those policies. So as long as your values are changing slowly, like your next value estimates would tend to lie close to the previous value estimates. And so you'd be following a policy that's close to there, and it might be more convenient for learning it because you're approximately on policy with the process of learning the values instead of being on policy with respect to the final result that you're hoping for.
To give a little more detail, so in the actual paper that we submitted to NeurIPS, there's like a theorem showing that the quality of the IPE behavior policy actually converges to the optimal value function. So the value function of the IPE policy goes to the optimal value function, assuming you can do value iteration exactly. More intuitively, though, what's going on is like imagine you had access to some value function, right, that actually corresponds to some policy. So what is the what is the IPE policy in this case corresponding to that value function? Well, it's exactly the policy that corresponds to that value function, because it is that policy that makes the Bellman error 0. So intuitively, you're sort of, if you're able to do value iteration, then you're tracking like the closest policy to the value function in value iteration. And yeah, and because like value iteration eventually reaches the optimal value function, the IPA policy reaches the optimal policy. That's just the intuition. Yeah.
Thanks, guys.
I think Rich is saying something, but
yeah, I don't think his mic is on.
I think he's muted, or no sound is coming out.
Dylan asked whether there's something in archive regarding this, and we haven't put it up there yet, but we could eventually. Policy. Okay, Alex is asking about elaborating on the connection between on-policiness and being close in value space. because two policies might be very far apart, but also be close in the space of value functions. Yeah, so like in this picture, I drew these circles, which sort of implies that the values are following some like Euclidean space, but in reality, it's not. But we do have a smoothness result where like changes in value represent small changes in the policy. So like whatever space the polytope is actually behaving in, like these small changes in values would correspond to small changes in the policy, and they would be nearby.
Hey, any chance you guys can hear me now?
Yes.
Okay, cool. Hey, thanks, Kris. You know, this, I just want to express, you know, the stupid question part of things, which is that I've heard this before and I'm still totally confused by it. And I mean, if you're doing value iteration is a control algorithm.
Mm-hmm.
And then you're also somehow aligning the policy to the current value estimate.
Yeah.
I don't see why that's a good idea. But I want to make another complaint first, which is that I hate the name inverse policy evaluation because it says it's explicitly asking you to think one way and then, oh, think the opposite of that. Why don't you name it by what it is rather than by what it's the opposite of? I think it will always make people be like I am, which are confused. If you call it the, you know, inverse something, it's not, call it what it is. I'm sitting here listening to your talk. I'm trying to translate it into a positive thing rather than into simultaneously think of the thing and then its opposite. So what would be the positive thing? It's sort of like it's aligning the policy to a value estimate. So it's a little of a policy alignment process. Can you express it positively in a way that would make it seem like it would be a good thing as part of value iteration?
Well, like I think that is a reasonable proposal. Like it is some sort of policy alignment process with the values. Like we just mainly like called it inverse policy evaluation and didn't really think too hard about alternatives. And we felt that it would be something that people were already familiar with, so like it wouldn't take too much like getting used to. But like policy alignment does sound reasonable.
So if you're using a policy to generate the value function,
Mm-hmm.
why does it make sense to then go back and try to align the policy with the generated value function?
Well, I guess like our intuition was that it was like on policy with respect to the current estimates, which seemed to be very convenient for, I guess, the path of or the trajectory that the value functions follow. But also it tends to be stochastic in a way that addresses like how poor the value estimates are. And so it ends up being exploring more in places where the values are poor and then exploring less in regions where the values are accurate and do satisfy the Bellman equation.
Why would it do that?
Like we sort of based it on this intuition of the policy's entropy. And like I guess most of our intuition is motivated empirically. We don't really know for sure whether this is actually happening. And that's why most of these little experiments we're trying to tease apart like why it's doing this or what it is trying to do. Because like we found that it is doing something, but I guess these are just our current thoughts on what's actually going on behind this.
I could see it as like policy iteration.
Yeah.
I greetify, do the value update, which is you greetify the policy in a value function, and then try to align policy to that greetified value. It's kind of like policy iteration.
Yeah. Like it's sort of doing that, but instead of jumping straight to the Or instead of tracking the greedy policy directly, it tries to track where it's currently at.
But it doesn't make sense as policy iteration, because if you did policy iteration, you evaluate a policy to get the value function, and then you try to align the policy to the value function. It's already going to be aligned if the policy iteration was all the way. So I'm a little lost. Yeah.
Well, I think that's assuming that you're jumping straight to the complete value function, or like you've evaluated the policy entirely, whereas this is interleaving it without finishing your policy evaluation.
Yeah. Yeah. Okay, thanks.
Can I ask a question?
Yeah.
How can you help me understand how you might use this?
So the main things that we've tried were to, I guess, use it for control like you would with like epsilon greedy or any other behavior policy. And it seems to be like, it seems to perform similarly to those, and sometimes better or easier to tune because it's automatically adapting this stochasticity. But alternatively, under this like intuition that like poor estimates seem to map to more stochasticity, like we also tried using it for hyperparameter selection as long as like the hyperparameter has some like probabilistic interpretation. But like, we haven't tried it beyond that. But I imagine that it could have some other uses.
Yeah. Can I ask a question?
Yes.
So one of the basic results in approximate dynamic programming says that as long as you improve your action value function in terms of like how far it is or how close it is to the optimal action value function, if you greedify with respect to that, the corresponding policy improves up to some degree.
Yeah.
Do you have anything similar?
I think Alan might be able to comment on that.
So I think we have two things that are somewhat similar. So we have one result on the difference between the optimal action value function and the action value function for any IPE policy, and that's a function. So it's basically, you can decompose that as the sum of your error in estimating the optimal action value function and the IPE objective. So in the course of optimization, you can drive both of those closer to zero so that the distance between the action value function of your IPE policy and the optimal action value function is goes to zero.
Okay. So
yeah,
so
it's definitely kind of hard to describe.
But like, so in a way, you have something similar to what I'm asking for, but not quite, or?
Yeah, it's similar, but not quite.
And if you don't have that, why not? So this is kind of like a smoothness, right? So if you go from action value functions to policies using greedification, then the suboptimality of the resulting policy depends in a smooth way on how close the action value function was to the optimal action value function. That's with greedification. So now you have a different way of deriving a policy from action value functions with this inversion process. And one must be wondering about, okay, like, is this stable in this sense or not? So you don't really know the answer to this, or you know it's not stable, or you know it's stable, and like if it's stable, do you know the stability coefficient?
So are you asking about whether like if there's some error in how you do value iteration, whether that error translates into some sort of bound or.
Yeah, it's like, forget about value iteration. You just have an action value function that someone gave you. And then if I'm given that, like, should I choose your way of picking a policy or a greedy policy? If I choose a greedy policy, I'm guaranteed that the return of that greedy policy is going to be 1 over 1 minus gamma times the suboptimality of the action value function that was given to me. So if someone gives me a better action value function, I'm guaranteed to get a better result eventually. The 1 over 1 minus gamma factor might be bothersome, but we know that with greedification, that's the best that you can ever do. So the question is, do you have can you have a similar result? Do you have a similar result? What do you know about this?
I think probably I'm going to have to think a little more about what you're saying, but like on the face of it, we do seem to have a similar result in that if there's some so say you have the optimal action value function plus some error. So we do have a result on the value function of the IPE policy of that action value function.
Okay.
So
what does the result say?
So the difference between the optimal value function and that value function.
Okay.
So it's just like a bunch of gamma terms plus error terms. So the error terms in the optimal action value function, and also this. Okay, I don't quite remember the notation. I'm looking at the thing I wrote down. There's another term that corresponds to the distance between your original IPE action value function and the optimal value function as well.
It seems, by the way, that okay, so you have the square error because you can't be sure that the action value function was derived from some policy. Yeah, but if the action value function was derived from some policy, then you would just get back the action value function of that policy, which is better. Yeah, which is much better than getting this 1 over 1 minus gamma blow-up factor. But I'm wondering whether this has the price that if the action value function was not exactly like the function that was handed to you was not exactly the action value function of any policy, then maybe there is a blow-up of the error.
Yeah, that's a good point.
And actually, okay, I guess in policy iteration, you would do this greedification, and you actually have the same result there. So you can refine the previous result saying that if you're handed over the action value function of a policy, then the next policy that you're going to get is at least as good as the previous one, if not better. So this doesn't quite feel that it's going to improve upon just greedification from this perspective. Anyways, I would be curious about what you have.
Yeah, I don't think we do guarantee monotonic improvement in that sense.
No, I think you can guarantee monotonic improvement in that strict sense, just by the fact that, I mean, like, you're not going to ruin anything, but you're not going to improve things. you can guarantee that. If you start with the action value function of a policy, then like this inversion process, if it's working, gives you back the policies, then nothing changes, like you're not ruining anything. But gridification actually, in this case, would improve, right? Or has the potential to improve. Yeah.
Like I think in the tabular setting, like point-wise, the greedy policy would be better than this policy.
Mhm.
But I guess like most of the benefits we were seeing were in, I guess, this iterative online setting where I guess it's using stochastic samples and like things haven't converged yet.
Mhm. Yeah. All right, thank you.
All right, so we've gone a little over time, so I'm going to ask everyone to thank the speaker, and Kris will stay back if people have more questions. Thank you, Kris.